in this NumPy library, there's a command for matrix multiplication. There is one critical mistake that you could make when it comes to doing matrix multiplication. So there's a command that you think might be matrix multiplication. And if you do it, the computer will not say anything. It'll just keep going and be like, yeah, it's cool, don't worry about it. And then it turns out everything's horribly wrong, and it'll be like horrible. So I want to see how many people answered that. Okay, let's find out. Reveal counts. Who answered the wrong thing? I don't know. Very good. Okay, I don't know. You're going to learn. Some people said matrix mult. I think matrix mult is wrong. If you type in matrix mult, the computer will go, I don't know what you're talking about. Okay. I don't know who's going to answer. NP matmul. I think that is a possible answer. There's more than one. Matmul is one. But let's see if anybody, I think I see the one that people did. I want to see if anybody did it. Aha, the most common answer. 3 out of 20 people put star. If you put in star, you're going to have a horrible time. You will be horribly, your code will run just fine, and you'll be like, why isn't it working? Everything is right. We multiplied it with a star. Star is not matrix multiplication. Star is entry-wise multiplication. So if you do a star, it will take all the entries of the matrix and multiply them together. So what it will do is it'll do like, here, let's get the blackboard over here. So it will do, if you do 1, 2, 3, 4 star with 5, 6, 7, 8, it will just multiply the things together entry by entry. So it'll do 1 times 5, and that will be 5, and then it'll be 2 times 6 is 12, 3 times 7 is 21, and 4 times 8 is 36, unless I made a mistake. That's not right, 32. Okay, great. So if you do star, your code, it looks like you have 2 matrices and they got multiplied in some way, and you won't know why your code is running wrong. So the most important thing you must know is that star is entry-wise, not matrix multiplication. And in fact, in NumPy, almost everything is entry-wise by default. You sort of have to be careful. If you want to do something that's not entry-wise, you got to make sure you don't accidentally do the entry-wise thing. Okay, so that being said, that's the main trap not to fall into. Let's see, what is the actual, what else did people say? I don't know, good answer. At, it turns out at is correct. If you do at, it will work. At is one possible answer, and matmul is the other one. Matmul, yeah, so if you did matmul or np.matmul, multiply, I'm not sure it would work. So matrix multi is close, you just shortened the wrong part. Okay, great. So if you do star, you lose. NumPy, you're gonna find out today. Mult, okay, I don't know. Okay, great. Lots of people are gonna learn about NumPy. So that's what we're gonna do all the coding in this course with, and all your assignments will be this coding. And it is technically Python, but the easiest way to do it is to go to this website called Google Colab. And it's like Google Docs for Python. If you hit new notebook, you will get a nice blank notebook where you can run your code. What is a notebook? A notebook is like a sequence of little blocks that all together make up your notebook, and the blocks can have code in them, so they can say like print hello world. You can run it by hitting this little play button, but once you get good at it, you'll learn that you do shift enter. So shift enter, so you can run that. And the other thing you can have in addition to code blocks is text blocks. And in the text blocks, you can type in math. So you can say like, oh, we're doing the vector p sub t. That's the vector of probabilities we care about. And then Google will render it for you as a little vector. When you type in the notes, this is Markdown. This is one of the ways you can do your note-taking assignment, is to type in the notes like this. Okay, so you can do code in Python, and you can do text blocks in Markdown. And we are interested in doing stuff with this NumPy library. So the first thing you got to do, import NumPy as np. That's the first command you will always do in almost every block. I guess unless you do hello world. Okay. And this will say, I'm going to use this NumPy library as np. And then you can make vectors and stuff like that by doing np.array. So we can make p0, that can be np.array, and Google will hopefully give me some suggestions. I want 1, I want 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I want 9 zeros. Let's see, did I get the right number of zeros? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, too many, okay. You're gonna delete 1. All right. So there's my p0. Does anybody remember what is P0 from last class? So again, we're in the snakes and ladders problem, and we're going to do it on the computer. What was P0, and why is it 1 and then 9 zeros? Does anybody remember? It's the initial state, right? So this is saying, look, the entries in this thing tell you the probability to be at any given state. In the snakes and ladders problem, we had square 0, square 1, square 2, all the way up to square 9. So this is square 0, square 1, square 2, all the way up to 9. And initially, before we start the game, at time 0, we have a 100% chance of being on square 0 and a 0% chance of being on all the other squares. So you should really read this as 100%, 0, 0, 0, 0, 0. You have a 100% chance of being in square 0. In programming, it's okay to use longer words. So maybe you should say probability vec initial or something like that. That would be a little more helpful. But I'm sure we did this last class, and I'm sure we called it P0. Let's check the blackboard. Okay, here we go. So here we had P sub t, and if t equals 0, then it's where you are initially. And I think we had these P0s. Yeah, here we go. Here's the update rule, and PT again. And okay, here is P. This is P1, right? Yeah, here we go. There it is. P when t equals 0 was the vector 1, and all zeros. That was from last class. And we got P when t equals 1 by doing this matrix multiplication with this big matrix, capital P. That is what I will do to get this, exactly what we did last class, running in code. So here we go. So that's our initial probability vector. And then I can do the probability one step. That will be the probability vector initial. And then you have to multiply by the matrix times the matrix P. That's the transition matrix. And that will work. Okay, I did two things that were wrong. One, Google has noticed. It's nice, it gives you a little red underline. It's just like in Microsoft Word. When you start typing and it doesn't make any sense, what's wrong with this? Yeah. I haven't told it what P is, okay. But I also made another mistake, which is I did star. If you do star, you go straight to jail, so don't do star. We're going to do at. Okay, great. So we got to tell it what P is, but then this will be perfectly great. And let's tell it what P is up here. And P is going to be a vector. Actually, let me make a new block. So P is going to be, I said it was a vector out loud. I meant to say it's a matrix. So actually, why don't we, again, let's give this a better name. Let's call it the transition matrix. It's going to be a matrix. You could write it all out. So you could say np.array, and then you could start typing away, and you could type in a 10 by 10 matrix. How do you type in a 10 by 10 matrix? You put in a big square bracket on the outside, and then in every single one, you put in a row. So you could do 10 rows. You could type in 10 rows that look like this, put them between square brackets, and if you type in the right things, which is this giant matrix over here, you will have the matrix P inside Python. You could do that. I'm going to show you actually how to get it a little bit more nicely. And to start with, I'm just going to make it all zeros, and then we're going to fill in the entries as we go. So np.zeros, and it's going to be 10 by 10. I can never remember if you're supposed to do 10 by 10 or if it wants one number, which is a 10 by 10. So we'll run it and we'll see. And it won't work if it doesn't work. I think it's the other way. Okay, yeah. You got to do 10, 10. Okay, great. Shift enter, run it. Okay, so I made it, and now it's a matrix with all zeros. One super good pro tip, and another good reason, even if you have Python on your own computer, you might prefer to use Google's, is Google gives you a little thing here called variables. This is the variable explorer. And if you open this up, it'll tell you all the variables that exist in your notebook that you've run so far and what they are. So I have this thing called P0, which is a 10 comma. So it's a vector with 10 entries. And if you mouse over it, it'll say, oh, it's the vector with 1 and a bunch of zeros. That's very nice. And you can check the sizes. This is the most useful thing, is to check the sizes. So if I go over transition matrix, you see it's an array, and it's shaped 10 by 10, which is what I expected, and it's all zeros. So it's written out all the zeros for me. Okay, we're about to fill in what the entries are. But this is a great place to pause for a second if there's any questions or comments. For some people, Python is the easy part of the course. For some people, the math is the easy part, and the Python is the hard part, and everyone in between. Question over here, yeah?
Not familiar with all that. How come you add a new box of code instead of just pressing enter?
Yes, I could do that. So if you want to add, you can make like a really long program, like all here, and then you could run that. And then it will sort of run everything in the code. So the reason I made a new line here is because I didn't want to rerun the probability vector initial. In other examples, you might want to do that. Very often you have like a block that sets things up, and then you have a block that does a bunch of stuff to the things you set up. Yeah, I guess when I sort of live code in class, I sort of go one line at a time. In your homework assignment, you might be going block by block instead. Fantastic question.
So you would prefer this way for the...
So actually, when you submit the code, you will...
When you say block by block, I wasn't sure.
Yeah. So when you submit the code, you will export it, and it will just put everything in one file. So I won't even know which one you did when you submit your final code. So sometimes it's nice to have it in a block. Sometimes it's nice to have it line by line. You can do whichever you prefer. And do also notice that if you run something, unless you restart the thing, it will remember what it is, right? So even though I renamed this thing to prob_vec initial, it didn't forget that I had a P0, right? So like I ran P0, and it was like, okay, got it. P0 is the thing you told me. And then I deleted that code, but it still sort of remembers what I ran. So that P0 is still around. If I wanted to get rid of P0, I could, so let me delete the nonsense code. You can go to runtime and hit restart and run all. Restart and run all, and that will, it's like, are you sure you want to restart? It's gonna forget all the variables you told it. And then I'm like, yeah, sure, that sounds good. And then it'll run everything again, and then it'll clear the situation, and now it's gonna yell at me because it doesn't know what capital P is. Okay, but now it forgot P0. When you submit your code, it has to work in a restart and run all because you're submitting it to a blank server. So the server starts with nothing. So if you have something and you ran it and then you deleted it and then you submit it for your homework, it won't work. Okay, good pro tip. All right, fantastic question. Anyone else? Yeah.
So is this the exact same format as Jupyter?
It is Jupyter, yes, exactly.
Okay.
Yes, that's right. And in fact, so some people have Jupyter on their local machine. The Google one is nice, again, because it has things like the Variable Explorer. It has little like AI suggestions. It underlines things. So it's, at least for me, it's smarter than my home one. The disadvantage is if you try to run it for like hours and hours, it will kick you off. It'll be like, hey, stop wasting my time. So if you have something super long to run overnight, then you probably put it on your home machine. Otherwise, I recommend Colab, and you can do the entire course in Colab. Yeah.
And then, so do you have just the import statements in the first block?
I mean, you could put them anywhere. Very often, you just have it once at the top.
You
And
just
then
have like one import statement.
That's right, yeah. Usually my first block is all import statements, everything I'll need, and then you run it once. Yeah. Yeah, great question. Anyone else? Okay, so we're gonna do the transition matrix, and instead of typing it all in, I'm gonna recreate what we did when we actually made it. So the transition matrix, remember it has this nice interpretation of the entries are the from to probabilities. So let's see if I can find. Here it is. Yeah, this is the big definition of the transition matrix. The S prime entry, so S and S prime are two different states in the Markov chain, two different states. And snakes and ladder, those are squares on the board. And the entry is supposed to be the probability to go from S to S prime. And so I'm going to use this interpretation to fill in the matrix. So I'm going to start it as all zeros. And then I'm just going to do a loop over all the entries. So if I was in math mode, I would say from S in range 10, because there's 10 states. And then I would say from S prime in range 10. And then I would fill in the thing here. Look, it's giving me a suggestion. Okay, transition. I never know what the suggestions will be. We're going to do S prime equals something. Equals, we're going to fill it in. So this would be how to do it in math mode. Okay, why is it yelling at me? All right, so this better be like this. I probably spelled it wrong. Transition matrix. Oh, I put in from instead of for. Okay, there you go. There's your problem. Okay. I was like, oh no, this is a disaster. Okay, okay, we got 2 for loops. Let's for now, let's make it 0.1. I don't know. That'll set all the entries to 0.1, which is a valid matrix. Okay, so this is the notation for loops. This is how you access an entry of a matrix with square brackets. And so this is telling it, go through all the entries, all the S values, all the S prime values, make it 0.1. If we did it right, when I go to my variable explorer, it should be all 0.1s. Okay, let's mouse over the transition matrix. And there it is, a wall of 0.1s. Very good, we're happy. Okay, that's not actually what we want. And here is a nice thing about programming versus math. When you do things, you can do things a little bit more intuitively. So first of all, instead of calling them S and S prime, which is the math notation, why don't I give them a little more explicit name? So I'm going to call it the from state, and this is the to state. And that's because, Oh, okay. You know what? Let me show you. There is a cool trick, which a student showed me last year. And let me see if I can remember how it is. There's a way, if you highlight this, it will highlight all the other S primes. And you got to press like Apple L or something. Does somebody know what it is?
Maybe Control R. Or Control M.
All right, I'm going to try Command L. Nope. Okay. If this doesn't work, I'll show you my second favorite pro tip for learning to code. Okay, I'm going to try Command Shift L. Let's see if that is that. Okay, it's Command Shift L, and now it has selected all the places that S prime happens. And now when you delete it, it'll delete it everywhere. So you can go delete, and then you put in to state, and you see you're typing in multiple spots. You can rename it everywhere. So that's a really good pro tip. Command Shift L, or I guess like Windows Shift L or something if you're on Windows. Okay, great pro tip. And then you don't have to do this annoying thing that I have to do now, which is make sure I don't forget this. Okay, so that's a good pro tip. All right, so we got the from states and the to states. You could fill them in. But instead of doing a for loop over all the to states, what I'm going to do is something a little bit smarter. I'm going to have no for loop there, and I'm going to do a different for loop over the dice rolls, the dice roll. And that a dice roll is in range 6. A dice roll is in range 6. And then I can just tell the computer to calculate the to state equals the from state plus the dice roll. And then it gives me a bunch of nonsense. Okay, there we go. So what this is saying is go through all the places that you can start in snakes and ladders, right? So you have your grid of 10 squares in snakes and ladders. For every possible place you can start, go through all the possible dice rolls. And where you end up is where you started plus the number on the dice roll. Okay, amazing. So now if you run it, what I want to do is I don't want to make this equal to 0.1. I want to add 1/6. So I'll do plus equal 1/6. And so what this is doing is instead of looping over the to states, I'm calculating the to states based on where the from state was. So this is like a really clever way. Instead of having a bunch of if statements like if the to state minus the from state equals 1, it's automatically figuring out all the possible to states. All the possible to states are the from state plus some amount of the dice roll, and then it's adding 1/6 to those. So if it was already increased by some other quantity, it goes up again. Maybe there's more than one way to get to a place. Questions? Yeah?
So what happened when we get to like never mind? Is there anything?
Okay. Well, actually, okay. I think you're about to preempt the next thing I'm going to say, which is, can you predict what will happen when I run this?
Oh.
Yeah. What do you think will happen when I run this?
Will we try to set up a out of bounds?
Yes. Okay. So this is a very good. So I'll let everyone else think for a second. When I run this, this will crash and it'll yell at me and it'll go, "You crazy idiot! You can't run that." So try to think of why. Maybe I'll give everybody like 30 seconds to try to think, what's the problem with this code? Why is this code going to break? Okay. Yeah.
I just have a question.
Yes.
How does it know what from state is to begin with?
So when you say for from state in range 10, what it is doing is looping over all the from state values from 0 to 10. So range 10 is a list of numbers from 0 to 10. Technically, it starts at 0 and it's length 10, so it's actually 0 to 9 inclusive. So in Python, this is how you do a for loop. In other programming languages, you'd say like for I equals 1 to whatever. This is how you do it in Python. Yeah?
You could technically still say for I in range, whatever. Just like
Yes, you could call the variable I instead of for state.
We're just fine with variables.
Yeah, right. But so the point is, there's no equals. It's in, and then over here is a list of stuff, and it'll loop through the stuff.
Okay.
Yeah. Okay. Fantastic. Yeah, this is great. So yeah, totally feel free to like part of the course is to learn to program and like put the stuff we're doing in math into programming. So you should feel free to ask these questions, and the sort of the difficulty will ramp up with the course. Okay. Great. Yeah. Another question.
So do you want for dice roll in range 1 to 7 instead of range 6?
Okay. That's a fantastic. That is a fantastic catch, and you are absolutely right. Right now, dice roll starts at 0 and goes up to 5. So it should be in dice roll in range 1 to 6 plus 1. So that is an honest mistake that I actually made. That, of course, that's just saying it's a dice whose labels are 0 to 5 instead of 1 to 6. It should still run. It'll give us the wrong answer. So that's fantastic. I'm really glad you caught that. I often write my range statements like this with a +1 to remind myself that the last number is not included, right? So if you say range 10, it won't actually give you 10. It'll give you 9, which is the largest square, so that's great. Over here, I want a 6, so I do 6 plus 1 so that it includes 6. Okay, fantastic. Really good catch. That's not the actual mistake. So there is an actual mistake where when I run it, it will not work. Let's run it and find out. what does the computer say? The computer says index 10 is out of bounds for axis 1 with size 10. This now is the moment where I can give you my pro tip, my second pro tip in 2025. How do you program? You copy and paste it into ChatGPT. Okay, let's see. Let's see what the computer is going to say. So this is, I think, the best way to learn to program if you don't know much. Let's make a new chat and say, what is the bug here? And it might not have enough information, but let's give it a go. Okay, the error means you're trying to access an index in transition matrix that is outside the allowable range, specifically on axis 1, and then it has some more stuff. But already I think this is a good hint in plain text of what this bug means, and maybe you guys have already figured out what is the problem with this code. There's a hand over here, maybe.
Two-state.
Yes.
It's not like it can go above 9.
Yes, okay, this is exactly the problem. So I thought I was being extremely clever by making two-state from state plus the dice roll. But of course, if you do that, the two-state might not be an allowed state, right? So you start on square 8 and you rolled 6 on the dice. Now two-state is 6 plus 8 is 14. That is not somewhere in the matrix where we can change. So two-state might be too big. And in fact, if you play this game in real life, you have to deal with this issue, right? If your piece is on square 8 and you roll a 6 on the dice, you have to decide what to do. And we talked about this last time. We said we're playing with the rule set that if you go over, then please make it the final state. And look, the AI has figured out what we're doing, and it says if the two-state is bigger than 9, then make it 9. That's saying if you were going to go over the last state, then instead you move to the final spot. So I just hit tab here, and the AI fills in what we wanted correctly. Let's make sure it's not doing something dumb. By the way, these AIs, they're very good. They're not always correct. You should treat it as somebody who is like trying to screw you over about 20% of the time. Sometimes it'll tell you like, oh, just change this parameter, and you're like, okay, I'll go change the parameter, and the parameter is like, oh, it doesn't exist. So like it will do that. It easily could have mixed up this 9 and it should be a 10 or something. I think in this case it's right. So 9 is the largest square. If you're bigger than 9, then make it 9. That should work. Question over here, yeah.
I'm not familiar with NumPy, but could you
Yeah.
also do two-state with like min from state?
Yes.
So that's roll on 9.
That would work as well. And if you want to do it in NumPy, there's a really nice command for this called np.clip. That is a really clever way to do it with a full like array or anything. So np.clip is a classy way to do it. So you would do two-state equals np.clip of two-state, and then you could do 9 two-state comma 9. It wants the minimum first. So it's telling me put the minimum and the maximum. So I guess the minimum value is 0 and the maximum is 9. And then that would make sure that it's between 0 and 9. If it's bigger than 9, it'll get clipped to 9. If it's less than 0, it'll get clipped to 0. So that's a classy way to do it. But I think the little if statement is nicer. Okay, great. So now it should work. Let's do it. Will it explode? Okay, so we got a matrix. We can look at our matrix over here. In the interest of making it easier to stare at, right now it's going to be a 10 by 10 matrix, and it's got a whole bunch of 0.16667s, which are a sixth. Right? Of course, it's supposed to do that. To make it a little bit easier to look at, I'm going to sort of factor the sixth out, and I'll just do +1 for now, so we can look at it, and then we'll add the sixth in right at the end. But this should be our matrix. Okay, there we go. So it's 1, 1, 1, 1, 1, 1, and then zeros, and then 1, 1, 1, 1, 2 zeros, and you see when you start getting to the end, you start getting things like 1, 1, 4, 1, 5, and 6. Actually, why don't I just tell it to print? That's another good tip. Okay, so you could say print transition matrix. Here's another pro tip for you. There's a really nice way to print things in Python in this situation, which is to use something called an F string. So you put an F and you put the thing in quotes, and then you put what you want, you put it in square brackets, or sorry, curly brackets, so like this. So this little F string command, what it will do is it'll take the value of transition matrix and replace anywhere it's between curly brackets, it replaces it with the matrix. So if you run it, you can get the matrix. And here's the really nice, the actual pro tip is to put an equals. And if you put an equals, it will include the variable name. So it'll say, transition matrix is this thing. This is a really nice way to have the computer print out your variables so you can see what they're like. And it's this kind of matrix. All right. Fantastic. Pretty good. Is that the answer we wanted? looks kind of similar, but not exactly. And that's because we forgot to do something. Can someone think of how you would fix this? So we're missing something. Yeah.
If it's 8, we have to put it 2. If it's 4, we have to put it
That's right. We haven't, so far, we have not included the snakes and ladders. But fortunately, in the way I've written the code, the snakes and ladders are kind of easy to see. The snakes and ladders, they do things if the to state, as I have written it now, is somewhere where there's a snake or a ladder. So if to state equals 8, another pro tip in Python equals is equals. So that's how you got to make sure you do that. And look, let me try doing something. Let me say there should be a snake down to square 2. I wrote this comment in to see if the AI will figure out what to do. Let's see. Ha! Okay, so the AI figured out if you're on state 8, then you should go to state 2. Very nice. Again, don't trust the AI. It will screw you horribly 20% of the time, but 80% of the time it's quite good. Okay. Similarly, yeah. Question over here?
Never. No, sorry. Where are zero indexing the to state zero index?
This is very important. Yes, Python is 0 indexed, and as it happens, the problem was also 0 indexed. So we're okay, but when there's a mismatch, you got to be really careful and not mess things up. That's a very good point. So just be careful that square 8 is actually the same as state 8. If they were different, maybe you could have a little translator function called like square to index or something, or index to square that translates and figure it out. Okay, let's figure out the last thing to do. That's the snake. We just need the ladder. And if to state, see, look, it's trying to guess where the snakes and the ladders are, which of course it has no way to know. So it's going to make it up and get it wrong. So if you trust the AI here, you will get like, it won't work. You'll be like, why is it doing it so bad? Okay, so the AI, what was that?
It's close.
It's close, yes, close. 0 points, okay. If to state equals, and it should be 4, because that's where the ladder was. There should be a ladder to square 7, I think. Square 7 here. Okay, and let's see. Yeah, there we go. So what it's doing is it's changing. If you actually would have gone to 4, then go to 7 instead. And that implements the snake and the ladder. And now we run it, and it will give us the matrix. Okay, I guess I'll go down here and run this to print it again. And that should be exactly the matrix that we had before. So it's got a bunch of zeros, 2 6s, a 5 and a 1, a 4 and a 1, a 3 and a 1, 1. Let's see if it matches what we did by hand last time. Hopefully it matches exactly. That should be what we got. Oh, actually, no, I lied. I forgot one thing. What's the one thing you got to put back? Yes, someone showed me with their hands. Amazing. You got to put back the 1 6. So here I'm sort of counting, right? How many ways are there? But I don't want to count. I want to find the probability. The transition matrix is the probability. Every single dice roll has a 1 6 chance. So what you should do is plus. Let's see if the AI knows this one. I'm very curious. 1 divided by. Okay, it doesn't know. 1 6. And in general, right? You're adding up probabilities. That's one way to do it. You could also do it with counts and then just at the end multiply by a 6th. However you want to do it, but it should be this factor of 1 6 in the front has to be there somewhere. All right, great, we did it. Amazing. Okay, and the print command works. Okay, so there you go. Now it looks really ugly because it converted all those things into nasty decimals. Actually, here's another pro tip. There's a way you can tell it to please hide some of the things when you're printing. What was it like? Let's see if I can remember this. First question, where's my mouse? np.set print options. How do I make NumPy show only 2 decimals instead of all the decimals? If you told it, I'm going to use np.print options, it would for sure get this. I'm curious if it'll get it without this. Let's see. np.set print options, and then you do precision equals 2. Great. So this kind of thing, if there's ever like, oh, there's some way to do this, like what's the way, or like how can you do some simple math thing in NumPy, ChatGPT is actually very good for this. Again, don't trust it 100% of the time, but it is quite good for stuff like this. Okay, so there we go. np.set print options precision equals 2, and then now when I run it, it will still keep all of the decimals, but it will only show me 2 decimals at a time, which makes it a lot easier to read and like make sense of. So like you'll notice, like this row, 0.17, 0.17, 0.67 should add up to 1, and it looks like it doesn't add up to 1, but it's only the output that it's showing us. Under the hood, it really does add up to 1. Okay, we got the matrix into NumPy. We're about to matrix multiply. Great time for questions. All right, so now we can do what we did last class, which is do these matrix multiplications. And you can do it with an @ symbol, transition matrix. Okay, and that will do the thing. Okay, and let's ask it to print it out. So print, and we're going to do the f string friend again. Prob at 1 step equals, and there's our vector. After 1 step, you have a 1/6 chance of being in all these places. But the nice thing, of course, you can now figure out the probability at any step. So we could do for t in range, 7, and we'll do probability. Let's say at t steps. At t steps, it's the probability at t steps. At every step, we do a matrix multiplication with the transition matrix, and then let's print it out. Probability at t steps equals. In here I can include t equals. I can do t equals this stuff, and then the probability equals that. So now it should print out line by line all different times. Okay, I got to start out with something. Probability at t steps when t equals 0 is the probability at 1 step, at initial. Okay, there we go. So 0 steps, and I guess this is starting at 1. Okay, there we go. Now it should work. Okay. So now we have a nice little list. So when t equals 1, we multiplied it 1 time. Then when t equals 2, we took what we had at t equals 1 and multiplied it again. When t equals 3, we took what we had before and multiplied it again. And you get this nice sequence, and it should kind of match the sequence we were starting to look at last time. So this is where you are after 1 step, after 2 steps, after 3 steps, and so on. It turns out there is a name for multiplying by the same matrix over and over again, which you've heard of. In fact, if it wasn't a matrix and it was a number, you heard of it in like grade 3. So instead of doing a for loop to figure out what's going on at the various times, does anyone have a suggestion on how you could do it differently? Yeah.
Exponent.
Yes, an exponent. Very good. So then you got to learn what is the command for matrix exponent, and we go to our friend ChatGPT. What is the command for a matrix exponent? This is exactly why it's useful to be a math person, because you know math, and then the computer knows programming, and if the two of you guys together can figure it out. Okay, for a matrix exponent in NumPy. Did I spell exponent wrong? What is this? linalg. Okay. Make it easier. Okay. Oh no, did it get mad at me? No, stop. Make it easier. Okay. Isn't there easy way? Import. See, it's doing some crazy stuff. Isn't there np.pow? I'm pretty sure there's np.pow. What does np.pow do? Okay, this is why you got to be careful with ChatGPT. Going to lead you down thing. Oh, okay, very good. I would have had it wrong. This is element-wise exponentiation. See, look, I would have fallen into the trap I told you not to fall into. Okay, great. So I guess we'll do it this way. Okay, you know what? Okay, you can do exponents some other way. If you want to do it, well, you can do it. Maybe I won't type it in the interest of time, so we can do some other fun stuff. But there we go. Basically, we've taken everything we learned from the last lecture, we've put it in the computer, and we're seeing how it works. Your homework assignment, which will be due at the end of next week and should be released soon, will be to do problems like this. So I'll tell you some rules variant of snakes and ladders, and you'll be playing around with these matrices, and you'll be writing programs that calculate these matrices and do things, and then you'll submit it, and the auto grader will check and see if it's right. Okay, we're about to do some new stuff. So this is a great question. Any questions about this stuff so far? All right, I do want to show you one other command in NumPy, which is yet another way to do matrix multiplication. and it is called the ein sum command. And so I'm going to do it with this thing. I'm going to rewrite this in a funny way, which is I'm going to write the same exact thing again using the ein sum command. It's np.ein sum. And then I'm going to type some stuff in here. And I'm going to do it on the probability, let's say stuff here. And then I'm going to do it on the probability vector initial and on the transition matrix. And if I type in the right stuff here, it will do exactly a matrix multiplication. But it can also do other things. It can do all sorts of crazy stuff depending on what you type in here. So I'll show you that in a second. Does anyone have a guess for what ein sum stands for? What the hell is ein sum? Yeah.
Einstein summation.
Yes, this is the Einstein of the, that student's name was Einstein, that same guy. So this is the Einstein summation convention in physics. And so this is the thing we're going to learn right now, is we're going to do Einstein summation. And the rule for Einstein summation is when you write an index, you sum over that index. And so as an example, when you do a matrix vector multiplication, so if you do P as a vector times the matrix M, and you say, please give me the bth entry, that will be the sum over PA times MAB. And you will sum over A going from 1 to N. So this is the row by column rule for matrix summation, right? So you go, in the P, you go by row, and in the N, you go by column. So this is matrix multiplication. If we were physicists, we could just write, this is the ordinary way, and the Einstein way is you just say PA, MAB, and they say, because you repeated the letter A, that means we're summing over A. So basically the physicists are just lazy and they don't write the sum. They actually work very hard and they have a lot of sums to write, so this saves them a lot of time. But the moral of the story, if you write A, AB, this means sum over A. So if you put in A, AB, this means sum over A, sum over A. Okay, so going back to what we actually wanted to do, we can put this in the Python directly by literally typing in this kind of thing. You put it in quotes, and it's a little string, and you tell the computer what you want to do. And if you put in A, comma, AB, that will work. That will work. And you can be even more specific, and you can say arrow B. And what this is saying is call the entries of this initial vector, call those A, and then call the entries of the transition matrix AB. And every time there's a repeated letter, we're summing over that. So this will do the sum exactly like I wrote on the board. It will do this sum. Where did the board go? So it's by writing A, comma, AB, it's doing exactly the sum. And the arrow B means store it in the bth entry of the output. So that means sum over A. And if you write A, comma, AB, arrow B, that means sum over A, and put the answer in the bth entry. Okay, so if you do this, it will be exactly the same as doing a matrix multiplication in this case. And you gotta spell things correctly. But then if you run it, it should give you the same thing. Okay, I suppose, to be fair, to make sure everything is working the way we think it is, let's run that. That's what the answer was supposed to be. Let's run this. And that's what the answer is if you do it with the Einstein summation, and lo and behold, they are the same. Okay, very good. Why am I telling you this Einstein summation? It is extremely useful for two things. One is when you get into situations where things start to get more complicated and you have like an array of vectors, then this is a really convenient way to organize things. So for example, here I did the probability at one step, but you saw very quickly I wanted to do the probability at t steps. And maybe I would put that in an array where the first index is the time and the second index is the state. So these A's and B's are kind of the states. You could call this like the from state and the to state, right? And then you could have a separate thing which is like the time. I guess T is already taken. Let's call time I for time, I don't know. And then you could do something like this. And that would tell it take the IF entry over here, sum over the F's, but leave the I's alone. So you can sort of control exactly what it's doing. As we go to harder problems in the course, this kind of thing will be useful. Another example, in this situation, the from state and the to state were numbers, right? We were playing snakes and ladders where there's square 0, square 1, square 2. Imagine we were doing something with like a knight moving on a chessboard. Then the from states have two numbers, right? The x and the y coordinate. So you could do something like take the xy coordinate over this and the xy coordinate over that and sum over and give me the AB coordinate like that. So if instead of being the states were being one number, if the states were two numbers, this kind of thing would come up. So this is a really incredibly useful command. And once again, it's a little bit hard to understand sometimes, but ChatGPT can help you generate these strings. Again, don't trust it 100%, but it's quite good at figuring this stuff out. So I'm mentioning that. It will come up later in the course. For now, you do not need to use it. But if you're interested in this kind of thing, you can do some digging and learn the einsum command. Okay. Questions or comments about einsum? The other reason we're going to use it, I'm going to rewrite this the way it was supposed to be. So it's the from state, the probability vector initial represents all the from states, and then the transition matrix is the from state to state matrix, and we're getting the to state. If you write this sum out like this, and we write it out like this, we're going to see a little mini proof of why is it true that this matrix multiplication rule works in the first place. So this kind of sum, if you unpack it, you will see that it is something about probability, and it sort of explains why our matrix multiplication rule works before. So last class, we justified it by, we did an example. Now we're going to sort of prove that this formula works by using this version of the matrix multiplication. So in other words, we're going to go to our Blackboard, and we're going to start with this, and we're going to have a little proposition, which I guess the proposition says, if you do the sum of P, so if P0 is the initial probability vector, probability row vector, and then you do the sum of P, I'll call it, let's stick with, let's do F's and T's, okay, from 2. PF, and then you sum over the from states in the possible states, and then you do capital P is the transition matrix, from state to state, then this thing equals, let's see, how should I say it? Let's call this the left-hand side, and let's call this the right-hand side. The right-hand side is the probability vector 1 at time 1 at position t. So prob vector at time t equals 1, so that's after one step. Oh boy, we've got multiple t's here. All right, let's switch back to A and B. Very sorry for people who are taking notes in pen. I thought I could be more nice, but I think it's just getting messed up. Okay, we're gonna do A's and B's. A, B at time t equals 1, and we're doing the bth entry. Okay. Then the left-hand side equals the right-hand side, and then you could also say i.e. P1 equals P0 matrix multiply capital P. So last class, we said this was true, and we sort of justified it based on the snakes and ladders example that we worked out by hand with Microsoft Excel, or I guess Google Excel. And now we're proving it with math. So it's just the statement that we're doing before, and you're going to see that the sum that we were just looking at is the key thing. All right, questions or comments about the statement of the proposition? All right, here is the proof then. So the proof. And it's one of those, a lot of people call a follow your nose proof. You just write down everything you know, and the proof will come out. So the left-hand side, it's equal to the sum of A and S. What is P? It's the probability that S0 equals A, right? So P is the probability vector, and the probability vector tells you the probability. So I'm just putting in what the definition of the probability vector is. It's at time t equals 0, because we said that was what is the P over here. So time 0, and that's because this P is P0. Maybe I should have put like 0 over here or something. Okay. Okay, but it's the time 0 vector. Where are you initially? What's the probability you're at position A? And then we're multiplying it by this probability, the probability you are at that S1 equals B given S0 equals A. And that is the definition of the transition matrix. So the definition of the transition matrix is if you start at position A and you do one step, what's the probability you end up at position B? Okay. All right. Yeah.
What's the set S again?
The set S. That's a great. So this was. Let me scroll up to last class. So S0, S1, S2 with regular S are which state you are in.
Right.
And I maybe didn't write this last class. Let me write it now. Script S is the set of all possible states. All possible states. So for snakes and ladders, it's 0 to 9. But if you were in some other thing, it would be over there. So yeah, it looks nicer on LaTeX. If you type it up, you do a /mathcal s, get a fancy script s, and these s's are the thing. Yeah, maybe I didn't say that last class. That's a great question. Yeah, so all possible states. Again, in this course, it's always a finite set. So you can count it up and number them 0, 1, 2, 3, 4, 5, 6, all the way up to some number. And so it's just doing the sum over all of those. Okay, yeah, great question. Anyone else? Okay, this sum on the board is a famous sum from probability. It is called the law of total probability sometimes. The law of total probability. Total probability. If you've ever done like Bayes' theorem, you have used this. Maybe you didn't know the word. Probability. And let me draw a little picture proof for you. So if this is your probability space omega, all the possible things that can happen, and it is cut into pieces. So there's piece number 1. Let's call this piece 1. Piece 2. Maybe not use P's for pieces. Let's use A's for pieces. A1, A2, A3, A4, dot, dot, dot. As long as the A's kind of are disjoint, so they don't overlap, and they span the entire space omega, so altogether they take up omega. Some people call this exhaustive. Then if you want to do the probability of some other event, B, the probability of B, it's equal to the sum of the probability of B and AI. And so what's saying is like, instead of doing the probability of B all together, you can cut it into little pieces. There's this little piece, plus this little piece, plus this little piece, plus this little piece. The law of total probability says that B has to be the sum of all these things. And the probability of B intersect AI also has another name. It's the probability of AI times the probability of B given AI. So in other words, what it's saying is, in this situation, maybe I should write down the hypothesis. The A's are disjoint and exhaustive. Disjoint because they don't overlap, exhaustive because they cover up the whole space. Then you have this rule that the probability of B can be split up into this big sum over conditioning on all the A's. And in words, this is very simple. It says, what's the chance that B happens? Well, if B happens, one of the A's has to happen. And then given that A happened, what's the chance that B happened? And because the A's are disjoint, you can just add up these probabilities. Like when you add up when I equals 1 or when I equals 2, they're completely separate events. If A1 happens, A2 definitely doesn't happen. So this is like something you use all the time. You just say like, if we want to know what's the chance that, I don't know, I get an A on my exam, well, I could have done it by getting an 80 or an 81 or an 82 or an 83. I guess this is assuming you're in a universe where A starts at 80. Okay. In any case, this is the law of total probability. You have the sum over these conditionals, and by the law of total probability, it's just the probability that S1 equals B. Woohoo, we did it, which is the right-hand side. So if you know the law of total probability, I guess it's a one-liner, and if you stop to explain the law of total probability, it takes a little longer. Okay. That's the proof in one slide. So the disjoint events here are what is the value of S0, right? S0 can either be A A or B, like it can either be one thing from the state space or another thing, but it can't be both at the same time. It has to be something. That's why they're disjoint and exhaustive. Okay. Okay, questions or comments about the proof? I guess it depends how much you like the law of total probability. Yeah.
So the law of total probability is the first orange line. Is the second line Bayes' rule?
Oh, I guess the second line. Okay, to me, this line equals that line is what people call the law of total probability.
Everyone seems like it's
This one equals this one is just the definition of the conditional probability. So the probability of B given A is by definition the probability of B intersect A divided by the probability of A, and if you rearrange it, you get this. So yeah, so this is a good point. Maybe we should remind the probability of B given A equals the probability of B and A divided by the probability of A. That's the definition of the conditional probability. If you plug that in, the A's cancel, you get the top. So it's just a rewriting that is convenient. Okay. So this law of the total probability is sort of why the matrix multiplication rule works. Again, we saw it last class in the spreadsheet. We said if you want to get to square 7, how do you get to square 7? Well, you either started on square 6 or square 5 or square 4 or square 3 or square 2. And then if you were getting to those squares, then you have to get to square 7 from there, and then you add them all up. So this is like what we were doing when we added up in the Excel spreadsheet. We added up to get the probabilities. It's exactly the sum, and it's the sum in the matrix multiplication or in the Einstein summation. It's always a sum. All right, very good. Questions or comments? Okay, now it is time for you guys to do some thinking. We got all the main ingredients we have here now. We got the probability vectors, we got the matrices, and I'm going to start doing weird stuff with them, and you got to tell me what it means, okay? And the first thing we're going to do is, so far, I've been kind of careful to say that the probability vectors are row vectors, and we're doing matrix multiplication on the left, right? So we said a row vector times a matrix. Now the question is, what does column vectors mean? What do column vectors mean? What do column vectors mean? That's the question we're going to try to answer. So row vectors, probability vectors are probability vectors. And the question is, what do column vectors mean? And I have come up with an example problem for you guys to try, which is the following. Where is it? Here it is. Okay, so in stakes and ladders again, think of P as the probability vector of where you are at some time. So you're playing the game at some time, you have the probability vector P, that's a row vector, and then I want you to do this multiplication with the vector 0, 1, 2, all the way up to 9. So that is a column vector, okay? And I want you to do some fill in the blanks here. So fill in the blank, the type of mathematical object is blank, and I think your options are like vector or matrix or things like that. And then I have a word where you can enter here. So in words, it represents the blank. You can do like 1 or 2 words in the word. So I want you to try to imagine what this is, write it out, and think about it. Of course, I will tell you, but it's good if you try it first and we see how you guys are doing, and it's good for your brain to remember it. Okay. Questions or comments about the question? All right, let me give you like 2 minutes to think about it, and then we will reconvene. Okay, there's not much time left. Who could use more time in thinking about this? Let me bump it up by another minute or two here. And let you guys think. I think if you write out what this is, like write it out as a big sum, will give you a good hint of what's going on. It might be something you recognize from your probability class. Okay, 2 minutes, but we really will stop at the end of 2 minutes. So put in, when it gets low, you can put in your guess. All right, let me get some water. Okay, there's like 15 seconds left. Put in your guesses. Once again, we can learn a lot from wrong guesses. So wrong guesses or guesses are good. If you really don't know, I don't know is also fine. Okay, there's like 4 people who are gonna beat the clock here while I press the buttons. But if I press the button, you'll be locked out and you'll be sad. Okay. Okay. See, I'm a bumbling idiot, so you got a little bonus. Okay. Reveal counts. Okay. All right. What kind of thing is it? 18 people answered. 13 people think it is a number. It is indeed a number. So if you said number, very good. Remember, we multiply row by column. So P is a row vector. Row and column, you go row by column. You stick them together, you get a number. It's also the inner product of the vectors P and this 0, 1, 2, 3 vector. So that's very good to know. I will warn you about one thing. So when we write math, we're very clear about row vectors and column vectors. One thing you're going to have to be careful of when you go to translate things to Python, there is such a thing as a vector where it doesn't specify row or column, and it will sometimes pretend to be a row vector and sometimes pretend to be a column vector. So if you go to the variable explorer, you will see, let me see if I have a vector here. You'll see it's a 10 comma. A 10 comma. So Python thinks this vector is just a vector with 10 entries, and it's not a 1 by 10, that would be a row vector. It's not a 10 by 1, that would be a column vector. It's just a 10 comma, and it will sometimes pretend it's either or. So you gotta be careful about that. If you wanna be extra super careful, you can tell Python, please make sure it's always a 1 by 10. But I'll show you the wrong way to do it in a second, where kind of bugs some people have. But okay, so row vector, column vector together, very good, is a number, fantastic, and it represents the blank. The blank. So we got dot product. It is definitely the dot product between P and this 0 to 9 vector. So that's absolutely true. Did some people say inner product? Inner product also means dot product. In this situation, the dot product or inner product has an interpretation as being the expected value. So that is also a correct answer. And average position, I also like that as well. That is also perfectly correct. So all these top answers are very good. Even I don't know, if you really don't know, is also a great answer. Not sure. Okay. Yeah, I guess put IDK, so you get put in the same bucket as the other people. Okay. So it's not a probability. Not a probability. Nope. You're gonna see something related to this coming up, but no. So expected value, fantastic. Average position, fantastic. Let's see why that is. Okay, so this is the thing. So we're doing P times 0, 1, ... 9, And if you write this out, right, this is really, it's the probability you're at 0, s equals 0. Probability s equals 1, dot, dot, dot. The probability s equals 9 as a row vector times 0, 1, dot, 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 9. And then when you do row by column, you multiply these all out. So you're going to get the sum. You're going to get the sum. Okay, let's write it without a sum. 0 times the probability s equals 0 plus 1 times the probability s equals 1 plus dot, 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 plus 9 times the probability s equals 9. Or if you want, it's a big sum. Let's call them x's, I guess. X going from 0 to 9 of x times the probability s equals x. This is also known as the expected value of s. The average value of s. So because the states here are numbered 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, it makes sense to just average them. And this is like the average of where you are, right? So sometimes you're at a high number, sometimes you're at a low number. Where are you on average? All right, so this is the first interpretation. When somebody does a column vector, they are talking about something to do with averages. So column vectors, you should think of as values. And if you do p times a v, so equals an average of the value. I'll have a little bit more specific mathy things to say, but for fun, let's put this in Python and compute where are you on average in our thing. Okay, so here we go. So I'm going to make this vector. Let's do it over here. So I'm going to call this v, and it's the array which goes 0, 1, 2, 3. It's the array that goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That would be perfectly fine. And once again, when you do this, Python is not keeping track of row vector and column vector. So it just says it's a vector with 0 to 9, and I'm going to just treat it however you tell me to. So if you do things correctly, this will work out. And I believe one way to do what we want is to do probability, let's say at one step, equals p at v. So that's a matrix multiplication, p at v. Okay, probability, that's not what I want. I want the probability at one step, the probability, and this is the expected value. Okay, and can you tell me what it is? Print f expected value. There we go, 3.999996. So after one roll of the dice, you are, on average, you're at 4, I guess. So, you roll the dice. I guess if you just roll a regular dice, after one roll, you're at 3.5. But because we got moved by a ladder sometimes, bumps the average up a little bit. That's why the average is 4. Of course, it's not perfect because it's just doing floating point stuff. But there we go. So that works. There's a bunch of other ways to do this. Instead of an at, you could do np.dot. I think that would work. So it's a dot product. And that would work. Again, yeah, I think Matt Mull. Will Matt Mull work? I think so. Or will it complain? Yeah, Matt Mull is fine. Yeah, let me think of... Okay, I guess in this situation, you can't really go wrong. In some situations, maybe you want to go the other way. Probability. So if you do this, right, if v is a column vector and probability at one step is a row vector, when you multiply them this way, you're supposed to get a matrix out. But NumPy, again, does not know about the row and column thing. So it just thinks they're plain old vectors. And so this will work perfectly fine, I think. I think it'll still output 3.996, even though mathematically it's wrong. Just something to be aware of. These like untyped vectors in Python sometimes cause problems. Maybe I'll just leave it the right way, and we'll come back to it later when we get to a real example where we have a bug. Then we'll know. Yeah, question?
I'm in the documentation. I'm not sure which
Yeah.
one, but NumPy also has a dot.
Yes.
In NumPy dot, you can speak that just a little.
Right, yeah. So again, there's a bunch of different ways to do it. Or you could do np.einsum, right? And you're like explicitly summing the probabilities times the values. Many different ways to do it, and it is good to know a lot of different ways to do it because sometimes tweaking them is slightly different in different ways. Yeah. Okay, yeah, fantastic. Any other questions? All right, so that's 4. That's an expected value. what else did I want to say? Okay, yeah, I wanted to, now that we know it's 4, you know what we could do that's fun? Let's do it in a loop. Remember, we did this for all the times. So expected value. Let's figure out what are these expected values doing. Yeah, there we go, at v, and let's also print it. Expected value equals, and now it'll print out everything. Ooh, I guess this is a big array. Let's do some new lines between them. So I'll make our output a little bit prettier. Let's see if it does what I want. Okay, so after 1 step, those are your probabilities. That's your expected value. 4, after 2 steps, 6.3. After 3 steps, 7.57, 8.2, 8.57, and so on. So you're sort of like, as you play the game, you're moving further and further to the right on average. Okay, fantastic. Let's do a little recap here of everything we've done so far. And I'm going to write down this expected value thing in a slightly different way. Yeah, okay, so this is true. Column vectors represent sort of values. If you do a product of a row vector and a column vector, that's an average. So as a probability times a value is the average of that value. And now here's the funny thing, which is we have this kind of thing. So we saw that pt equals p0 times the matrix p to the power t. So if it's true that the probabilities come by multiplying on the right with the matrix, then what would happen if we do pt times v for some column vector v? Well, that would be p0 times pt times v, right? So when you do probabilities, you update it by doing matrix multiplication on the left. When you want to do an expected value, let's call this expected value. Then you do pt times v, that's p0 times p to the power t, the big matrix, times v. And you can see that sort of in here, we are multiplying pt times v on the other side, right? So v is a column vector, we're multiplying the matrix p on this side. And so you could think of, this pt-v combination, either you can think of it as p0 times p to the t, and then with a v on the end, or you can think about it the other way. So there's sort of 2 equally good ways to put the brackets. p0 times p to the t, all times v, or the other way. These are 2 equivalent ways to do matrix multiplication. You can do them you can put the brackets however you want, all right? So you might remember that matrix multiplication, you can't switch the order, but you can switch the brackets. So the brackets, that's called associative, and it is associative. And these are 2 equally good ways of thinking about it. It turns out one of these things is called the Kolmogorov forward equation, and one is called the Kolmogorov backward equation. Kolmogorov forward equation, and the other one is the Kolmogorov backwards equation. And they have nice interpretations. So it's 2 ways of thinking about how do the probabilities evolve, and you can either think about it with thinking of the probabilities as the thing, or the expected values as the thing. And I realized I think I have the arrows backwards. I think these, I can never remember which is which. Okay, let me switch the arrows. I think this is the forwards and this is the backwards. Okay, let me write them another way. So the forwards equation, this is the one that we already did. And it says, it says that the probabilities evolve according to matrix multiplication on the left. So this is the last proposition we did. So we already did that one. And it was just saying that the probabilities evolve according to this pt matrix by multiplication on the left. The fact that p0 times p to the t equals pt, that was exactly what we did before. So that's this proposition all the way up here. Of course, this proposition was only with t equals 1, right? So to make it really true, you got to take it, apply it t times, but that is the Kolmogorov forward equation. Let's write down the Kolmogorov backwards equation, and it says something like this. So it says, if you want to do the expected value of v of st given s0 equals, here I'll write it out as a big vector. So this is a big vector, v of st given s0 equals 1. Let's write it out as a giant vector. And it's a giant, the point is that it's a giant column vector, s0 equals, let's call that n minus 1, where n is the number of states. So this is a giant vector. These are the expected values, given that you're starting at 0, starting at 1, starting at 2, all the way up to starting at n. So this is kind of the reverse of how we were looking at things before. Here we want to know, given where you start, where do you end up, and what is the value there. This giant vector, so this is a n by 1 column vector. Let's call this thing the left-hand side. And the right-hand side is the product. It's the matrix p to the power t times v, where v equals v of 0, v of 1, dot, 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 v of n minus 1. So what this is saying is that if you do p to the power t times vector v, it tells you these expected values. And these expected values, it turns out, will be really important later in the course. So as we go to the course, we're going to be looking at this picture way more often than the reverse picture. And that's because these values are going to encapsulate the rewards, right? Remember, the whole reason we're doing this is to learn about rewards and actions. And we're going to say, how much reward do we get? We're going to put that into a function called the value function. And then we're going to try to look at how the value function is evolving on average using this kind of thing. So the Kolmogorov backwards equation says that you can get it by doing matrix powers of p to the t times v. Let me show you what that looks like in code. Okay, maybe I'll pause for a second here for questions or comments about this. It really is just saying, look, instead of multiplying the probabilities and then doing v at the end, first do p times t times v, and then do the matrix product there first. Okay. Again, you can also prove the left-hand side equals the right-hand side by the law of total probability, this time with expected values. Questions? Okay, let's do it in code and see where that gets us. Okay, so what do I want to do? I want to do powers of the matrix P times V. So let me copy this this kind of pattern over here. So a bunch of different t values, and I'm going to do the expected value t steps into the future. And it's the transition matrix times V at V. Okay, so just like before, we're multiplying by the transition matrix every time. But instead of multiplying the probabilities, we're multiplying the expected values. And I guess this thing starts at V. So it starts at V. Okay. It is not defined. Expected value. All right, and then I guess I want to print it. Okay, so here we go. What did V start as? Is V what I think it is? V, okay, V is this, okay. Okay, great. So what this is telling you, right, why is this one a 4? Why is this one a 4? Remember, we saw that if you start the game in the 0th square and you roll the dice once, where are you on average? You're at 4, right? What happens if you start on square 1 and you roll the dice? Well, you're going to be at 5 on average. So it has all the different starting spots in it, right? That's what was written in the sort of math over here. right? So the thing that is varying in the vector is the starting location. Where did you start from? And so if you start from square 0, you'll be at 4 on average. If you start from square 1, you'll be at 5 on average. Square 2 is 5 on average. And you see that the further you start, the bigger you are. And if you start on square 9, after one roll, you're still on square 9. You're still at 9 on average. If you multiply by many values, you get where are you on average after that many rolls. So this is t equals 1, t equals 2. Let's say at t equals 2, after 2 rolls, if you started at square 0, you're at 6.39. If you started at square 7, you're at 8.33. So 7, this is square 7. So if you start on square 7, you're almost certainly, right? If your average is 8.33, you must be 9 a good chunk of the time. So if you started on square 7, most of the time you'll have 9. Your average is very close to 9. Does anyone know why it's not exactly 9? Why is it a little bit less than 9? You start on square 7, you roll the dice, you're hoping to get square 9. Just, your average is a little bit under 9, which means you're not fully there yet. Let's look at, we got to remember, what does the snakes and ladders board look like? By the way, I don't know if anybody noticed this. ChatGPT, one of the last things I looked for, snakes and ladders, how do you draw it, right? So I had the snakes and ladders written in some other thing, and I was like, please make this a nice little thing. And that's how we got this little beautiful picture over here, another ChatGPT. So you start on square 7, you're trying to get to square 9, you've rolled the dice twice. Why are you not always at 9, right? Right? The minimum outcome for rolling 2 dice is 2. So you should always be at square 9. Why are you not always at square 9? Yeah.
Because of the snake.
Yeah, so when you roll a 1 on your first one, you go back down to square 2. So your average is only 8.33. You're 9 most of the time, but a little bit of the time you've fallen down the thing. That's why your average is only 8.33. So this sort of backwards way of looking at things, it's going to come up more and more. We'll start off with that next class, and we'll use these kinds of calculations to calculate more things in our problem. All right, I think it's a perfect place to stop. See you guys on Thursday.